In this video, we discuss a concept called state machines, and state machines turn out to be a very powerful organizing principle in designing logical circuits for different applications. So we're not going to do the formal state machine, which is actually quite interesting, but as an introduction, we're just going to look at constructing a simple device, and then we're going to use that simple device as a way, or we're going to use state machines as a way of designing that simple device. So the device is the following. It's a single push button lock that to lock and unlock a door. So if we push the button to unlock the door, we push the button again to relock the door. And so it's a door lock controlled by a simple button. Okay, so let's look at a little bit more detail on this. When you push and then release, so push and release is an important thing here, a button, it will unlock the door. To relock the door, you simply press and release the button again. So this is just, it's a fairly simple device. Now, before we try designing it though, because we're going to design it with logic circuits, we want to think about actually how this door lock works in very, very formal way. And so we're going to come up with a sequence of short statements that define the operation of this lock. So how does this lock work precisely? Now, in order to make this sequence a little bit easier, you may assume that the door is initially unlocked and the button is unpressed. So this is where we're going to start our state. So why don't you pause the video for a moment and see if you can come up with a sequence of statements that define exactly how this door is going to work. I hope you actually did come up with that sequence. And so let's go through and see how your sequence compares to my sequence. And so our task was to build a one-button door lock, and so I repeat the requirements here. And so I'm going to just number the sequence of events. So initially we're going to start with the door unlocked and the button is not pressed. That was our assumption. Okay, so we're just going to stay there until the button is pressed. So until the button is pressed, we're just not going to move. We're just going to be unlocked until the button is pressed. Now, while the button is pressed, the door is going to remain locked. Now, why is that? Because we press and then release the button to unlock the door. So from this rule, we jump down here when the button is released. So previously the button was pressed. That's how we got here. Then we're going, when the button is released, the door is going to unlock. Now, the door is going to remain unlocked until the button is pressed again. And then while the button is pressed, the door remains unlocked. Why? Because this is the same press and release requirement we had in our door lock. And then finally, when the button is released out of this condition, okay, the door is going to lock. Now, when at this state the button is released or unpressed, the door is locked. Isn't that the same situation as we have up here? So we can simply return here. So you could probably write a little program that does this. What we're going to do is we're going to write that program, quote. We're going to write the quote program in logic gates. So we have this as a formal way of expressing our door lock. You may have had a different way of doing it, and make sure that your way gives us the same behavior as the one I propose here. So we're going to begin this by defining states. Okay, and a state is actually a formal mechanism for talking about where this door lock is at any particular point in time. So we're going to define 4 states, and the state is going to be the door is locked and the button is unpressed. This is the first state, and I'll call it state 0. Generally, we number states from 0. The second state is going to be the door is locked, but the button is pressed. And then the third state is going to be the door is unlocked now, and the button is unpressed. The third state is going to be the door is unlocked, and the button is pressed. And then from the third state, we go back to the 0 state. So the lock actually works by going around this circle of states in a clockwise manner. And so we're going to then say, well, how do I go from state 0 to state 1 or state 1 to state 2? And so let's take a look at that. This is the whole concept of state transitions. So we're going to go from one state to the other. So our rule was we start here in state 0, and then we're in the situation that we're locked and the button is unpressed. As long as the button is unpressed, we stay in that state. So that's indicated by this little circle with an arrow on it. So if the button is unpressed, we just stay in this state. We just continue in this state. However, when the button is pressed, we transition to state 1. And so what do we do in state 1? When the button is, as long as the button is pressed, we stay in state 1. And then when the button is unpressed, we go to state 2, and so on. Now convince yourself that this state transition, as we go around this circle, is identical to the set of rules that we put on this door lock. If it isn't, then we've made a mistake. So I'm going to use a more compact notation because that diagram was pretty big. So here's what I'm going to do. I'm going to say for each one of the states, I'm going to find the state of the lock, which is over here. In this case, the lock it's locked, and the state of the button. In this case, with the bar over here, the button is unpressed. And so then I'm going to say as long as the button is unpressed, remember this is this P bar, we stay here. If the button is pressed, notice we just use a P symbol for that, then we transition to the next state, and then we go around. Inspect this, and make sure that this is the same state machine that we described in the earlier diagram. So we're just using L and P as variables. Okay, we're going to use 4D flip-flops to hold the state. So now we're going to talk about implementation. And so what happens is state 0 is represented by the state of this D flip-flop. When Q0 is 1, we're in state 0. State 2 or state 1 is represented by this flip-flop, a second flip-flop, and when this is equal to 1, now we're in state 2. And then this flip-flop is holding, it indicates we're in state 2, and then I'm sorry, I got these wrong. When this one is 1, when Q1 is 1, we're in state 1. When Q2 is 1, we're in state 2. I was counting from the wrong state. When Q3 is 1, this indicates we're in state 3. So this is how the flip-flops. We're going to assume that all clock inputs are connected to a common clock. So all of these will change. All these flip-flops will change at the same time. Okay, so let's talk about state transitions. Well, before we talk about state transitions, let's look at an important part of the state transition, which are these circles. So let's take a look at what happens if we want to stay in state 0. Well, what happens if we want to stay in state 0 is that we have to be in state 0. Okay, so this is a 1, and we have to have the button unpressed. So this is P bar. So the button is unpressed, we're in state 0, and then what would happen? D0 would be 1, and so when the clock rises, what's going to happen? We stay in state 0. Okay, so how do we leave state 0? Well, we leave state 0 when P becomes 0. When P becomes 0, then this AND function says we have a 1 here, a 0 here. Now D0 is going to be equal to 0, and now we'll transition from a 1 to a 0, so we'll leave that state. The same argument will hold for the state 1, which would be this loop, state 2, and state 3. So now we have a simple logic gates that will go through and keep us in the state until it's time to leave the state. And the way that we leave the state is on whether we have the button is pressed or the button is not pressed. That determines it. Now the question is, how do we move to the next state? Okay, so we know how to stay in a state and how to leave a state. That was the previous slide. So let's look at it. We're going to move from state 0 to state 1, which is this transition, when the button is pressed. So we will enter state 1, okay, by setting D1 equal to 1. Okay, and that means that D1 will be equal to 1 when Q1 is 0, or Q0 is 0. In other words, we were in the previous state, and the button is pressed. So this will cause us to transition from Q0 is equal to 1 to Q1 is equal to 1. Okay? Convince yourself that to go from state 1 to state 2, we just implement this logic function. And then to go from state 2 to 3, we implement this logic function. And then to return back to state 0, we have to be in state Q3, which is Q3 is equal to 1. And we have to unpress the button, which would be P bar. So this allows us to move from state to state. So now we actually have two things we have to incorporate in the construction of the Ds, okay, of the inputs to the D flip-flops. The first thing we have to talk about is, how does a D flip-flop remain in a state? And that's done by these statements. So this is the input to the state 0 flip-flop, the input state 1 flip-flop, the input state 2 flip-flop, and 3 flip-flop. So in order to remain in a state, we have to implement this function. And this also, this term allows us to leave the state. And then to cause the flip-flop to enter a new state, we will use the results from the previous slide and say that we will enter, let's say, state 0 if we were in state 3 and the button is unpressed. So what this does is we can actually implement each one of these logic, these rows with something like this. So let's look at D2. D2 says that we need Q2 and the button is not pressed, or P bar, okay? And we need the AND of those, which is actually done right here. Or we need Q1, that we're in state 1 and we're transitioning, which is this part, and that's implemented here. It's an OR function between these, because either one of these would cause the D2 to be 1, so we would simply place the OR function here. So these three gates will produce D2. Now, we got a little bit of a problem though with this, and so let's take a look at this in a little bit more detail. Is that what happens is that the way we've implemented it, it takes 3 gates to implement each one of these inputs to the D flip-flops. I want to simplify this, and the way I simplify it is the following. Let's look at the term for D0. D0 is Q not and not P, and or Q3 and not P. Can't I factor this? So I'm going to use a little bit of Boolean algebra to factor this. So I can go through and deal with it this way. So it's an or with an and rather than 2 ands and an or. Okay, so I can do the same one to the other inputs to the D flip-flops. So now each term is going to be simplified by just rearranging these algebraic terms, these Boolean algebraic equations, is that we or the states that we're interested, and then we and them to the state of to the whether this button is pressed or unpressed, and then this gives us the input to the D flip-flop. So we saved an AND gate on this thing. We can do the same thing. This is producing D0. We can produce D1. I would like you to spend a few moments and draw the schematic diagram for states 2 and state 3, just to make sure that you understand how to do that. I hope you figured it out. It's almost a pattern that you can come through, so that the entire state machine now can be represented in this form. So we have the ors and the ands, and everything looks pretty good. So actually this state machine, or these 4 circuits, when combined, would implement this state machine, which is quite cool. It would just basically, the state will go from this machine to this this flip-flop to this flip-flop, and then return to that flip-flop. So it's kind of cool. The one thing we forgot on this is how do we get these the signals that we called P, which is the state whether the button is pressed or unpressed, and L, whether the door is locked or unlocked. Okay, and so P is actually relatively easy. We're going to have the switch here, and so when the switch is unpressed, because we have a resistor pulling up to +5, this point is going to be +5, which is a 1. We pass that through an inverter, and so it says that this switch is 0. The switch is unpressed. We pass it through another inverter. This says the switch P bar is 1. So this says 0, 1. The switch is not pressed. When the switch is pressed, we'll put it down here, we now ground this point. So now this is a 0. Now this is going to be equal to a 1, and this is going to be equal to a 0. So this is a nice little circuit to indicate whether the switch is pressed or unpressed. Some of you may say, well, why can't we just take this junction, move it up here if I can, and call this P bar, so we could get rid of this inverter. Okay, the reason we don't do this is it's really nice to have any signal that's generated by a resistor and a switch to pass through a logic gate before we use it. And so we would really like to go through and use the 2 logic gates, the 2 inverters, so we make that signal compatible to the logic family we're dealing with. Now, how do we use an LED to indicate that the door is locked? Okay, so we need a function, and I'm just going to call this function a logical function. I'm going to call it question mark, that combines the 4 states to produce the value of L. So we want this to be a 1 when the door is locked, and hence the LED will lock. And so these are the four states we're combining. There should be a comma here. And so we inspect that state machine, and when do we want the door to be locked? We want this to be a 1 whenever we're in state 1, or state 0, or in state 1. So L is just equal to this. It's just a simple OR function. And so we can build it with an OR function. Now, we have the design of the design for P and L now. Okay, and so we know that we need two inverters to get L and one OR gate to get to get P and one OR gate to get L. This requires the addition of an inverter chip, one inverter chip, and one OR chip to our circuit. Now, we would like to change the design so we can do both functions. In other words, for P to do P and L on one chip. Now, how can we do that? Well, we can use a NAND gate or NOR gate to make the P. Why? Because we know that an inverter can be implemented by either an NOR gate or a NAND gate. This is a NOR gate, and this is a NAND gate. So we know that we can make an inverter this way. Now it seems like it's kind of ridiculous that we use a NOR gate to build an inverter, but it may be just more efficient if we had a leftover NAND gate or NOR gate. And remember, these are NAND gates and NOR gates because they have these little circles out here, right? They invert this before they do anything. Okay, so now this becomes a harder part. Can we implement the L signal with an AND gate or OR gate? Well, we start out by saying that the lock signal is just the it's the OR function of the two states. We can negate both sides. It's a little bit of Boolean algebra, and then we can use De Morgan's law. De Morgan's law says that this expression, the invert of two states the invert of an OR is equal to the AND of the inverse of each one of the inputs. Now this is De Morgan's law. By negating again, we can find that L is just equal to the NOR of the this is the NOR part, okay, of the inverse of each one of the inputs. And so we can do this. So guess what? We turned our OR function that we had up here, okay, into a NAND, or into a NAND function. Why is it a NAND function? Because this is an and this is the circle that's at the end of it. So we can now use NAND gates to do both the L and the P signal. So we can check to see if our design's correct, because this sounds pretty bizarre. So we started out, okay, we think we can make L with this circuit. Okay, is that the same as the OR function that we know we need? We begin by the truth table of the NAND function, which is the truth table of this. So if an output C is equal to the NAND of A and B, we know this is what it looks like. Okay, so that's what we have. If we substitute Q0 and Q1 for A and B and L for C, we would just get this table, okay, through the NAND function. And then just if we, instead of Q naught and Q1 naught, we will go through and just replace that with Q0 and Q1, which means we're going to negate this to get this. We get the inverse of this to get that, and so on. What is that? That's just an OR function. So indeed, we found that this is true. So our circuit checks is implementing an OR function with Q1 and I'm sorry, OR function of Q0. Right here, this should be Q0 and Q1. Okay, put this together. This is what we have. We can generate the L with or the P with just this is just an inverter, and this is another inverter, and then we can produce the L with just using this NAND gate. So we got it. And then you say, but hold it, don't we need to get Q1 bar and Q0 bar? And no, because these are outputs of the D flip-flop, so we already have them. Okay, so we showed that we can actually build this thing, okay, and by simplifying the P and L. Okay, by the way, it's also possible to half the number of flip-flops, which we're not going to do, so don't worry about it. We're almost done. Is that the current way that we define the state is we use 4 flip-flops. These are the flip-flops. These are the states. And notice we just have a flip-flop. One flip-flop is set at any particular time. If we use 2 flip-flops, we can encode the state by basically using this counting function. State 1 is indicated by one of the flip-flops or both flip-flop being reset. State 0. State 1 is when one flip-flop is set, the other one's reset, and so on. And so the question is, then we would need to change the way that we transition from one state to the other. But now we only have 2 flip-flops. So we're going to make the state transition a little bit more complicated, but we save on the number of flip-flops, which is pretty important. We're not going to do that, but we're going to talk about a general state machine. This general state machine looks like the following. Let's go in the center of it first. First of all, we use some kind of memory element to hold the state. And so I have n of these memory elements. Okay, I just used a D flip-flop. What happens, the memory elements have the input to these flip-flops are being generated by some big piece of logic. So this is logic here. And the logic can be either gates or it can actually be done with some kind of a read-only memory, which is actually pretty cool. And so what we do is we return the state to the logic. So the logic has state, and we indicate the state by this vector, which we call Q. And then the logic also has inputs. So this would be, for example, button presses and these kinds of things, which will express by a vector I. So this is a concatenate vector of Q and I. Now, we have a state transition matrix, which is a group of ones and zeros that would indicate how we generate the D vector. And the D vector is basically all of the signals going out to the D flip-flops. So we have a clock that runs here. And at that clock, this logic will produce the D inputs to the flip-flops depending on the current state, which is the Q, and the current inputs, which is the I. An output matrix against the Q vector, the current state, will give us the outputs on this. So this was a very formal way of establishing one form of a state machine. Okay, this is we're going to be using D flip-flops, and again, this is the output of the this is the pin out we're going to use, and I think this is it's a 4013. It has 2 flip-flops, so it's got a flip-flop down here on this side and a flip-flop on that side. We've done it before. And so this is your assignment. Design a 2-button door lock Okay, and so the first thing you have to do is to figure out the the key uh, presses that, or the button presses that will cause this door lock to open. So it could be, for example, button 1 followed by button 2, button 1 followed by button 1, button 2 followed by button 1, whatever. Go through and define. This would be the key for this. Have the door lock. So this would be to unlock or light. Okay. Have the door unlock when the buttons have been pressed properly. Okay. And have the door button lock. Okay. When both buttons are pressed simultaneously. And you can build this. Okay. I suggest you do it first because it's simpler, and then you can expand it in any way you wish. So it's been a long video, but I hope it's been interesting as you understand how to use state machines to design something more important than just ones and zeros.